Inside a factory somewhere in the American Midwest, a block of titanium is being stripped down layer by layer until it becomes a structural component for a commercial aircraft. The allowable tolerance is measured in microns, many times smaller than the diameter of a human hair. This part will sit in a load-bearing section of the airframe, where even a tiny geometric error can become a stress concentration point. And in aerospace materials, a stress concentration point is the kind of thing no one wants to explain in front of an accident investigation board. The machine operator does not look nervous. The machine in front of him has cut thousands of parts like this without drifting out of tolerance. But look closely at the logo on the casting, and it is not Cincinnati, the name that once dominated the American machine tool industry for nearly a century. It is not Bridgeport, the brand that became almost a generic word for vertical milling machines in North American shops. The logo carries a Japanese name, Makino. That becomes even more remarkable when you remember what happened in 1986. That year, the United States government signed voluntary restraint agreements with Japan and Taiwan, a rare form of trade intervention that forced those countries to limit their machine tool exports to the American market. Washington did this because the American machine tool industry was being devastated by Japanese competition, and policymakers increasingly saw the issue not merely as business, but as national security. Barriers went up, doors closed. Buy American sentiment spread across machine shops, especially those serving defense and aerospace customers, where the origin of production equipment was a sensitive question. And yet, nearly 40 years later, suppliers to Boeing, medical device manufacturers, and die and mold shops across the United States treat Makino as a benchmark for their most difficult work. How did a Japanese company, born in a country that once had to import much of its machine tool technology from the West, cross both trade barriers and cultural suspicion to become trusted inside some of the most demanding corners of American industry? The answer begins in Tokyo in 1937, with a man who believed that the only road worth taking was the hardest one. If you want to follow this full journey, and more stories about the machines that built the industrial world, make sure to like the video and subscribe to the channel before we turn back the clock. To understand where Makino came from, you first have to picture what Japanese industry looked like before the Second World War. That picture was far more modest than the image of a manufacturing superpower we know today. Japan in the 1930s was industrializing at extraordinary speed, but it was doing so on a borrowed foundation. Its shipyards, weapons factories, locomotive works, and engine plants relied heavily on machine tools imported from the United States and Germany. When a Japanese workshop needed a precise milling machine, it ordered one from overseas, waited for it to cross half the world by ship, and then learned to operate a piece of equipment it could not yet build for itself. Domestic machine tool production existed, but it was thin, fragmented, and often treated by Japanese customers as a second-choice alternative to Western machines. This was not a minor technical inconvenience. It was a strategic weakness, and Japan's industrial and military leaders understood it clearly. Machine tools occupy a special place in every manufacturing economy because they are the machines that make the machines. A country can import cars and still have a transportation system. It can import steel and still build cities. But a country that cannot build its own machine tools never fully controls its own manufacturing capability. Japan's militarization and industrial expansion in this period created enormous demand for metalworking equipment, and the gap between that demand and domestic capacity became the driving force behind a new generation of Japanese machine tool builders. Set that starting point beside the position of the United States at the same time, and the gap becomes enormous. Across the Pacific, the American machine tool industry stood near the height of its power. Cincinnati was a manufacturing center for an entire continent, producing milling machines and grinders that helped define industry standards. Monarch in Ohio was building precision lathes so accurate that, only a few years later, the U.S. government would reserve some of them for secret weapons programs. Bridgeport in Connecticut was about to release the vertical milling machine that would sell in the hundreds of thousands and become the training ground for generations of machinists. America did not merely lead in output. It had the entire ecosystem: foundries, supplier networks, trade schools, and a domestic market large enough to sustain hundreds of builders at once. In the eyes of the global machine tool industry, Japan barely appeared on the map. In that imbalance, one truth became clear to Japanese engineers with a long view. If the country wanted industrial independence, it had to start with the machines that made other machines. There was no shortcut. A nation could not forever assemble final products using equipment built by someone else. And in 1937, in Tokyo, an engineer named Tsunezo Makino decided to place his own stone in that foundation. In 1937, Tsunezo Makino founded Makino Milling Machine in Tokyo. The name itself stated the ambition plainly. This was not a general-purpose machine shop trying to do whatever work came through the door. It was a builder of milling machines, stepping directly into the category that Japanese factories still depended on the West to supply. The company's first product was the Type A vertical milling machine, recognized as the first vertical milling machine designed and built in Japan. In the industrial history of a nation, milestones like this are often overlooked because they are not glamorous. But their meaning is very concrete. After the Type A Japanese shop looking for a vertical mill had at least one option that did not have to arrive through a seaport. What matters most is not simply that Makino built a machine, it is how he positioned it. The Japanese market at the time, like most industrializing markets with limited capital, favored inexpensive machines. Small workshops bought equipment with carefully saved money, and the natural logic for sellers was to cut cost as aggressively as possible in order to offer the lowest price. Tsunezo Makino chose the opposite path. His philosophy, what we would now call quality first, could be reduced to one principle: the machine should be more accurate than the customer required. Not accurate enough to sell, not merely accurate enough for the market to accept, more accurate than the buyer expected. It was deliberate over-engineering. From a conventional business perspective, this was difficult to justify. Over-engineering meant higher cost, higher selling prices, and a harder fight in a price-sensitive market. But Makino's logic came from a deeper understanding of what a machine tool really is. A machining center is not a consumer product. It is a productive asset that may stand on a factory floor for 10 years, 20 years, sometimes longer, and every part it cuts over that lifetime carries the mark of its quality. A cheap but unstable machine does not truly save the customer money. It simply moves the cost from the purchase invoice into scrap, adjustments, downtime, rejected orders, and lost trust. A machinist might not calculate that equation on the day the machine is purchased, but after years of operation he will understand it, and when he understands it he will remember which name did not betray him. From the record available, we know that Tsunezo Makino came from an engineering background and began on a small workshop scale, like many machine tool founders of his generation in both Japan and the United States. We do not need to invent unverified anecdotes about him, because his real legacy is not found in legend. It is found in the decisions the company made over the decades that followed. Whenever Makino stood at the fork between cheaper and more precise, it turned toward precision. That philosophy would be tested by war, reconstruction, numerical control, and most brutally by a trade war with the United States. Remember the principle that the machine must be more accurate than the customer requires, because it is the red thread running through the entire story. It explains why, when some competitors fought downward on price, Makino fought upward into difficulty. And it helps explain why, nearly 40 years after the voluntary restraint agreements, some of the hardest titanium parts in American aerospace are still cut on machines bearing the name founded in Tokyo in 1937. To understand why Makino became a name trusted by American aerospace shops, you have to return to a moment when the very meaning of accuracy in machining was being redefined. In the late 1940s, at the Massachusetts Institute of Technology, a project connected with John Parsons helped give birth to the idea of controlling machine tools with numerical data rather than by the hands of the operator alone. Numerical control, or NC, was still a laboratory technology, bulky, expensive, driven by punch tape, and supported by electronic cabinets that could take up half a room. The United States possessed the invention. But invention and commercialization are not the same thing, and the space between them is where Makino entered the story. In 1958, Makino successfully built Japan's first NC milling machine. Put that date in its proper context. Only 2 decades earlier, Tsunezo Makino's company had been a small Tokyo workshop that had just produced Japan's first domestically built vertical milling machine, in a country still dependent on American and German equipment. 13 years earlier, Tokyo had been in ruins after the war. Yet by the end of the 1950s, that same company had brought numerical control, a technology only recently emerging from the world of MIT laboratories, into a domestic commercial machine. This was not simple copying. It was the ability to absorb technology at a speed few outside Japan believed possible at the time. But the 1958 milestone only matters if you understand how NC changed the nature of machining itself. Before numerical control, accuracy lived in the hands of the machinist. A skilled operator could feel cutting force through the handwheel, hear chatter in the tool when the speed was wrong, and stop exactly on the mark of the dial. That skill took years, often decades, to develop, and when the machinist retired, much of it retired with him. A factory that wanted to expand had to find more people like him, and people like that could not be produced in large numbers overnight. NC changed the equation completely. Tool paths could be encoded as data, and data could be copied endlessly. The 1,000th part could match the first, regardless of who stood beside the machine. In other words, NC moved precision from the body of the worker into the body of the machine, and once precision belonged to the machine, the company that built the most precise machine could control the value chain behind it. Makino understood this earlier than many of its competitors. 8 years later, it took an even more important step. In 1966, Makino introduced Japan's first machining center. The difference between an NC milling machine and a machining center sounds technical, but in business terms it is the difference between a tool and a production system. An NC mill still required the operator to stop the machine and change tools by hand between operations. Every time a human hand interrupted the process, error had a chance to enter. A machining center integrated automatic tool changing. The machine could move from roughing cutter to finishing cutter, from drill to reamer, completing a sequence of operations in a single setup. The fewer times the workpiece was removed and refixtured, the more reliably the geometry between surfaces was preserved. Repeatability, the ability to produce the same result over thousands of cycles, became something that could be promised in a contract rather than simply hoped for. This is where Tsunezo Makino's 1937 philosophy found its technological form. He had chosen over-engineering, building machines more accurate than the customer demanded, in a market that preferred low price. With manual milling machines, That philosophy remained partly an article of faith, because the final result still depended heavily on the operator's skill. With NC and machining centers, it became measurable. How tightly could the machine hold tolerance? How many times could it repeat the same cut? How many hours could it stay stable? Makino did not invent numerical control, and it never claimed to. What it did was become the first Japanese company to turn an American-born invention into a domestic commercial machine, and then use that foundation to build a reputation that would one day travel back across the Pacific and win over America itself. But for that reputation to endure, Makino had to win another war, quieter and far less visible, against an enemy the naked eye cannot see. Ask someone outside the industry what determines the accuracy of a milling machine, and the answer will usually involve cutting tools, motors, or control software. Ask an engineer who has lived long enough with micron-level tolerances, and the answer will be different. The real enemy of precision machining is heat. Metal expands as it warms and contracts as it cools. At the scale of microns, 1/1000th of a millimeter, that expansion is not a minor detail. It becomes a force governing everything. A machine structure made of cast iron and steel changes size with every degree Celsius. A high-speed spindle generates heat in its bearings. Ball screws generate heat through friction. Motors generate heat. Even sunlight coming through a shop window in the afternoon can warm one side of a machine more than the other, quietly distorting its geometry. This phenomenon is called thermal distortion, and it explains a familiar paradox in machine shops everywhere. A part cut at 8 in the morning is within tolerance, while a part cut at 2 in the afternoon drifts out, even though the program, tool, and operator have not changed. The only thing that changed was the temperature of the machine itself. This was the battlefield Makino chose for its reputation, and that choice says a great deal about how the company thought. Thermal stability is the kind of engineering no one sees at first glance. It does not appear in easy advertising numbers like spindle horsepower or rapid traverse speed. It lives inside casting designs that distribute heat symmetrically, in mass placed exactly where it can absorb vibration, in solutions such as core-cooled ball screws, where the ball screw is cooled from within, so frictional heat is neutralized near the point where it is created, rather than allowed to migrate into the machine structure. It lives in the quality of the spindle, the heart of the machine, where the smallest deviation is transferred directly into the surface of the part. All of these things add up to a difference you only fully appreciate after hours of continuous cutting. A machine that is merely good enough can remove metal. A Makino is built to keep that metal inside micron-level tolerance through an 8-hour shift, from the first part to the last. That difference had a very specific customer base, the die and mold world. A plastic injection mold or metal stamping die is not the final product. It is the tool that creates hundreds of thousands, sometimes millions of other products. Every flaw in the mold surface is multiplied across the entire production run. The more perfect the mold surface, the less hand polishing is required afterward, and hand polishing is one of the most expensive and skill-dependent stages in the entire mold-making process. That is why die and mold shops are willing to pay a premium for hard milling, the direct milling of hardened steel, a technique that only becomes practical when the spindle is strong enough and the machine structure stable enough to cut harsh material without chatter or deflection. Alongside hard milling, Makino also built a strong position in EDM, electrical discharge machining, a process that uses sparks to erode deep cavities and complex shapes that cutting tools cannot easily reach. Together, hard milling and EDM made Makino a name closely associated with mold making. The business mechanism behind the technology is essential. Die and mold customers, like aerospace customers, do not pay for horsepower alone. They pay for stability. For them, A failed part is not merely wasted material. It can mean a mold delivered late, delaying an entire product line, or an aerospace component rejected in an industry where almost good enough means complete rejection. In that calculation, the purchase price of the machine becomes a smaller variable. The cost of instability becomes the large one. By concentrating its engineering on precisely what these customers needed most, Makino placed itself in a segment where price competition mattered far less. This was a lesson many American machine tool builders of the same era did not learn quickly enough. When you sell stability rather than iron and steel, customers do not abandon you simply because another machine is 20% cheaper. But there was one barrier that engineering alone could not overcome: politics. And the way Makino handled that barrier became one of the smartest moves in the company's history. By the early 1980s, trade relations between the United States and Japan in machine tools were moving toward confrontation. Japanese machines, with standardized controls, improving quality, and competitive prices, were taking over the American market at a pace that stunned domestic builders. Names that had dominated American machining for half a century began to weaken, merge, or disappear. Anger in the industrial world turned into political pressure in Washington. Anyone watching the situation could see what was coming. Sooner or later, the U.S. government would build a barrier. For Japanese builders, the question was not whether the barrier would come, but what to do before it arrived. In 1981, Makino gave its answer, and it was unlike the others. Instead of simply accelerating exports while the window remained open, Makino acquired a controlling stake in LeBlanc Machine Tool, a long-established lathe builder from the Cincinnati, Ohio region, right in the heartland of the American machine tool industry. The new entity became LeBlanc Makino, with its North American headquarters in Mason, Ohio. Pause on that image for a moment, because it contains the irony of the age. At the very moment American opinion was turning against Japanese machine tools, a Japanese company bought a century-old American machine tool name, retained an American workforce, kept an American base, and began producing machines on Ohio soil. The value of the deal had several layers, and the most obvious layer was not necessarily the most important. LeBlanc gave Makino customers, a sales force, service experience, and a name that American industrial buyers had known for generations. But the deeper layer was legal and psychological. A machine produced in Ohio, by workers in Ohio, inside a company paying taxes in Ohio, no longer fit neatly into the category of imported Japanese machine, targeted by both trade restrictions and Buy American sentiment. Makino did not try to jump the fence. It changed passports. In this case, acquisition was that passport. History soon confirmed the logic of the move. In 1986, the United States signed voluntary restraint agreements with Japan and Taiwan, limiting the number of machine tools entering the American market. This was an unusual level of intervention by Washington into a civilian industry, and it reflected the desperation of American builders at the time. For many Japanese manufacturers, including companies such as Mazak and Okuma that were still largely seen through the lens of imports, the restrictions were a real squeeze. For Makino, they almost served as confirmation that the investment made 5 years earlier had been exactly right. While competitors had to calculate quotas and face suspicion, Makino already had manufacturing, engineering, and service rooted inside the United States, serving American customers with the response time of an American company. To be historically fair, there is no evidence that Makino knew in 1981 the exact timing or details of the 1986 agreements. What can be said is that the company read the wind correctly. Trade tension was visible from the beginning of the decade, and Makino responded with long-term commitment rather than short-term tactics. manufacturing in America was more expensive than exporting from Japan. It was more complex to manage and more difficult culturally. But it bought something no pricing strategy could purchase: the status of an insider. When an aerospace supplier or a mold shop in the Midwest needed a machine, spare parts, or an applications engineer on site within 24 hours, Tsunezo Makino in Mason, Ohio, could respond in a way an importer's representative office never could. Looking back, the Ohio move perfectly connects the two halves of the Makino story. The first half is engineering, NC in 1958, the machining center in 1966, the battle against heat and vibration, all of it creating a product worthy of trust. The second half is strategy. Even the best product needs a path to the customer. And when the front door is blocked by tariffs, quotas, and suspicion, Makino bought another path, legal, durable, and located on the customer's own ground. The question from the beginning of the video: why some of the most sensitive shops in American industry came to treat a Japanese name as a benchmark after the trade restrictions of the 1980s, now has the first half of its answer. They were not simply buying from a distant Japanese exporter. They were buying from a company that had built, hired, serviced, and planted roots in Ohio before many of its American competitors vanished from the map. The other half of the answer lies in what happened next, when Makino had to fight on two fronts at once, against anti-Japanese sentiment in America and against its own countrymen. The Ohio move had barely taken shape before the storm arrived. In the first half of the 1980s, the American machine tool industry suffered one of the fastest and most brutal collapses in its industrial history. Names that had once been the pride of machine shops, from Monarch in Ohio to Cincinnati Millicron in LeBlanc's own region, began to shrink, sell off divisions, or disappear. Imports, much of them from Japan, captured more than half of the American machine tool market in only a few years. Washington was forced to do something a market economy rarely likes to admit in public: intervene to protect a dying industry. In late 1986, the Reagan administration announced voluntary restraint agreements with Japan and Taiwan, limiting the number of milling machines, lathes, and machining centers allowed into the United States for 5 years. In the press, Japanese machine tools were described as a threat to national security. In machine shops, anti-Japanese sentiment moved from purchasing offices down onto the shop floor, where workers had seen colleagues lose their jobs as American factories closed. For most Japanese builders, that barrier was a wall. For Makino, it became almost a shield. Thanks to the LeBlanc acquisition in 1981, the company already had a factory, engineering staff, and service network in Mason, Ohio before the barrier went up. While competitors counted import quotas, Makino could assemble, finish, and support machines on American soil, employ American engineers, and pay taxes in Warren County, Ohio. The phrase Japanese machine lost some of its force when customers realized that the person arriving to tune their spindle lived only a few dozen miles from the shop. But clearing the political barrier was only half the fight. The second front opened from home. Mazak, Moriseki, and Okuma, Makino's Japanese peers, were sweeping global markets with a different formula: highly standardized machines, large lot production, delivery measured in weeks rather than months, and a CNC ecosystem that Fanuc had turned into a common language for the industry. A shop owner in Chicago could order a Moriseki machine today, receive it in 6 weeks, and put operators on it with minimal retraining because the control interface was familiar down to the individual keys. This was the weapon that had helped defeat many American builders, and now it was putting pressure on Japanese builders that chose a less standardized path. Then a third front appeared inside the United States itself. In 1988, at a trade show in Chicago, a former California machine shop owner named Gene Haas displayed the VF-1 with a publicly listed price of $49,900, less than one-third the price of many imported machining centers. Haas did not compete through refinement. He competed by lowering the cost of entry into CNC machining. The lower end of the market began to drop beneath the feet of everyone standing there. Pressed from three sides at once, Makino faced the familiar choice of every manufacturer in crisis: move down in price or move up in difficulty. It chose the second, with a consistency that almost looked stubborn. Instead of building cheaper machines, Makino concentrated its engineering on work where the phrase "good enough" had no place: 5-axis machining for aerospace structures, hard milling of hardened molds, EDM for die and mold applications, medical components, and semiconductor-related parts where tolerances are measured in microns and a single mistake can condemn the entire workpiece. The T-Series was developed for titanium, a material that is both elastic and intensely heat-generating during cutting, demanding high-torque spindles, vibration-absorbing structures, and cooling strategies ordinary machines cannot provide. The MAG series targeted monolithic aluminum aircraft structures, where more than 90% of the original billet can become chips, and material removal rate determines the economics of the entire job. The business logic behind this decision was cold and simple. In the lower end of the market, customers compare purchase prices. In the upper end, customers compare the cost of one failed part. A titanium bulkhead for a fighter aircraft can carry more value in material and machine time than the price difference between a cheaper machine and a Makino. Destroy it in the final operation, and every saving from the purchase decision can evaporate in a single afternoon. In that world, repeatability and thermal stability are not marketing specifications. They are risk insurance, and buyers will pay a premium for that insurance. Haas could not follow Makino into this segment, and the other Japanese builders had to divide their strength across a wider market. Makino narrowed itself into the deepest part of the field, where competition was not decided by the price sheet, but by the tolerance chart after 8 hours of continuous machining. 4 decades after the voluntary restraint agreements, look back at the names in the industry. Monarch, the lathe builder that equipped the U.S. Navy through 2 world wars, sold its lathe division in 1997. South Bend went bankrupt in 1992, and the brand eventually passed to an importer. Fadal, the California-made VMC star of the low-cost segment, closed its Chatsworth factory in 2008 after years of ownership changes. Cincinnati Millicron withdrew from machine tools and turned toward plastics machinery. Meanwhile, machines carrying the Makino logo stand in the shops of aerospace suppliers, die and mold makers, and medical device manufacturers across North America, and the people operating them do not treat that as a compromise. In many mold shops, the standard process for complex mold cavities is almost built around Makino high-speed hard milling and EDM. In aerospace structures, automated cells running multiple shifts with little or no direct supervision have become one way American contractors keep contracts under global cost pressure. The paradox from the opening now has its answer, and that answer points to a principle larger than any one company. A brand does not survive on nationality. It survives on engineering discipline. Reputation flows from engineering. The machinist on the floor is not loyal to the flag printed on a catalog. He is loyal to the machine that still holds a part within micron tolerance in the 8th hour of a shift, to the ball screw that does not drift when the shop temperature changes, to the company that still exists to supply parts after 20 years. American builders did not disappear because they were American. They disappeared because, at decisive moments, their engineering discipline was pushed behind other priorities, sometimes corporate structure, sometimes price, sometimes shareholder expectations. Makino endured not because it was Japanese, but because the choice Tsunezo Makino made in 1937 was never reversed. Return to the beginning, and the circle becomes clear. In 1937, in a country still borrowing machine tools from America and Germany, an engineer opened a workshop in Tokyo and built Japan's first domestic vertical milling machine, guided by the unfashionable belief that a machine should be more accurate than the customer demanded. In 1958, that company brought numerical control into Japan's first NC milling machine, shifting precision from the hands of the machinist into the machine itself. Then it declared war on thermal distortion and vibration, the invisible enemies of precision machining, before much of the market understood why they mattered. When the trade storm arrived, the company that had chosen the hardest path turned out to have the most options, enough engineering reputation to move up into high-end work, and enough strategic foresight to already be standing on American soil when the import door began to close. The hard road chosen in 1937 became the only road still intact when the industry changed hands. And so, tonight, in a machine shop in Ohio, a Makino spindle is still turning, peeling titanium from a part that an American aircraft may carry for the next 30 years, or cutting through hardened steel for a medical device mold that will help create something placed inside the human body. The operator standing beside it may be the second generation in his family to work in this trade. His father may once have read angry headlines about Japanese machine tools in the middle of the 1980s. But he does not ask where the machine is from, any more than anyone asks the nationality of a law of physics. He only knows that when the shift ends and the gauge touches the part, the number will be right. In this industry, that is the final definition of trust. From a small Tokyo workshop in 1937, in a country still dependent on the world's machines, to a benchmark of precision inside some of the most demanding factories in American industry, Makino answered the question from the beginning of this story with a formula that had no shortcut, engineering discipline preserved across 9 decades, and an Ohio move made 5 years before the trade barrier came down. If stories about the machines that built the industrial world are what you want to hear next, like the video and subscribe to the channel. See you in the next episode of the Gear Archive.